Have you ever stared at a star and wondered what you're really looking at? That tiny pinprick of light seems so simple, so peaceful, so insignificant. But what if I told you that every star you've ever seen is a raging nuclear inferno, so violent, so powerful, so incomprehensibly massive that it makes every explosion humanity has ever created look like a firecracker compared to a supernova? And here's the thing that's going to blow your mind. That peaceful twinkle you see on a clear night? That's ancient light from a thermonuclear furnace that's been screaming across the void of space for years, decades, centuries, sometimes thousands of years, just to reach your eyes. You're not seeing stars as they are. You're seeing them as they were, looking back in time every single time you glance at the night sky. And that's just the beginning of how strange stars really are. These aren't just hot balls of gas floating in space. They're cosmic alchemists, transmuting elements through processes so extreme that they literally warp the fabric of space-time around them. They're time machines, showing us their past with every photon that reaches our eyes. They're factories, manufacturing every atom in your body through nuclear reactions that release more energy in 1 second than humanity has consumed in its entire existence. And they're ultimately the reason you exist at all. Because without stars, the universe would be nothing but a cold, dark void of hydrogen and helium, incapable of producing anything as complex as a molecule, let alone a living being. I'm about to take you on a journey that will completely transform how you see those distant lights. We're going to explore stellar nurseries where stars are born in violence and chaos, where clouds of gas larger than anything you can imagine collapse under their own gravity to ignite nuclear fusion. We'll witness the lives of these cosmic giants as they burn through fuel that would power human civilization for trillions upon trillions of years, maintaining a perfect balance between gravitational collapse and explosive fusion for billions of years. We'll watch them die in ways so catastrophic that they forge every atom in your body, creating elements that couldn't exist any other way, scattering them across the cosmos to seed future generations of stars and planets. And by the end, you'll understand why the most profound truth about stars isn't just that they exist, but that without them nothing else could exist either. Not planets, not life, not you. You'll discover that every breath you take contains atoms that were once inside multiple different stars. Every thought you think is powered by energy that originated in fusion reactions at the sun's core. Every solid object you've ever touched is made from stellar debris. The screen you're watching this on, the chair you're sitting in, the ground beneath your feet, all of it is recycled star material. You are not separate from the stars. You are the stars, rearranged into a form capable of wondering about stars. But before we dive into the cosmic furnaces themselves, let me give you fair warning. What you're about to learn will fundamentally alter your perception of reality. The physics we're dealing with is so extreme that it defies every intuition you have about how matter should behave. We're talking about temperatures where atoms can't exist, where electrons are stripped away and matter becomes a soup of charged particles. We're talking about pressures so intense that quantum mechanics becomes the dominant force, where particles tunnel through barriers they shouldn't be able to cross, where the very structure of space-time begins to warp and distort. The timescales are so vast that human history becomes less than a blink. While you've been alive for a few decades, stars have been shining for billions of years. While human civilization has existed for maybe 10,000 years, some stars will continue burning for thousands of trillions of years into the future, long after our sun has died and the Earth has been consumed. The smallest red dwarf stars will still be shining when the current age of the universe has passed 100 times over, and the implications, well, they're going to make you question everything you thought you knew about your place in the cosmos. you'll realize that you're part of a cycle that's been repeating for over 13 billion years, that your atoms have been through multiple stars, that you're a temporary arrangement of matter that will eventually return to the cosmos to be recycled again. The calcium in your bones was once inside a star that exploded billions of years ago. The iron in your blood was forged in conditions so extreme that they only exist for milliseconds during a supernova. The oxygen you're breathing right now was created inside a massive star that lived and died before our solar system even existed. So if you've ever wondered what stars really are, where they come from, how they work, and why they matter more than anything else in the universe, then buckle up, because what you're about to discover will change everything. You'll never look at the night sky the same way again. You'll never feel sunlight on your skin without remembering that you're feeling the output of nuclear fusion happening 93 million miles away. And you'll never forget that you are, quite literally, made of stars. Every single atom in your body, heavier than hydrogen, was created inside a star. You are walking, talking stardust. Let's start with something that seems simple. What is a star? You might think you know the answer. It's a big ball of burning gas, right? Wrong. Stars don't burn. They don't combust. What's happening inside a star is so much more violent, so much more powerful than simple burning that comparing them to fire is like comparing a candle to a nuclear bomb. Actually, that's not even close. A nuclear bomb is closer to a candle than a star is to a nuclear bomb. The difference in scale is that extreme. Stars are fusion reactors. At their cores, temperatures reach millions of degrees. We're not talking about the kind of heat you can relate to. This isn't oven temperatures or even the surface of molten lava. We're talking about temperatures where matter can't exist in any form you'd recognize. At their cores, temperatures reach 15 million degrees Celsius. That's 15 million. The center of the sun is about 250 billion times more pressurized than Earth's atmosphere at sea level. Under these conditions, the very laws of physics that govern your everyday experience stop applying in ways you'd expect. Atoms are crushed together with such force that their nuclei, which normally repel each other with electromagnetic fury, are forced to merge. You see, atomic nuclei are positively charged and, like charges, repel. Under normal circumstances, you could never force two hydrogen nuclei together. They'd push apart like trying to force the same poles of two magnets together. But in the core of a star, the temperature and pressure are so extreme that nuclei are moving so fast and colliding so violently that they overcome this electromagnetic repulsion. This process, nuclear fusion, converts mass directly into energy, according to Einstein's famous equation E equals mc squared. And because the speed of light squared is an enormous number, even tiny amounts of mass release staggering quantities of energy. Let me put this in perspective. Every second, our sun converts about 600 million tons of hydrogen into helium. That's 600 million tons every single second. In the process, it loses about 4 million tons of mass that's transformed into pure energy. Just gone, converted from matter into light and heat and radiation. That's the mass equivalent of 1 million cars vanishing every single second, converted into light and heat that radiates out into space. 1 million cars worth of mass just ceasing to exist as matter and becoming energy instead. And this has been happening every second for 4.6 billion years. 4,600 million years. That's longer than the Earth has existed. That's before complex life emerged on our planet. That's before the dinosaurs. before anything more complex than single-celled organisms. The Sun has been doing this without pause for longer than multicellular life has existed on Earth, and it will continue for another 5 billion years before our Sun runs out of fuel. 5 billion more years of converting millions of tons of matter into energy every second. By the time the Sun finally exhausts its hydrogen fuel, it will have converted roughly the mass of Saturn into pure energy, an entire planet's worth of matter, transformed into light that spreads across the solar system. But here's what should really mess with your head. The Sun is just an average star. It's so ordinary, so middle of the road, that astronomers literally classify it as a yellow dwarf. It's not special. It's not particularly large or small, hot or cool, bright or dim. It's just average. There are stars out there so massive that they make our Sun look like a marble next to a beach ball. UY Scuti, for example, has a radius about 1,700 times larger than the Sunday. Let me say that again. 1,700 times larger if you placed UY Scuti at the center of our solar system. Its surface would extend beyond the orbit of Jupiter. Mercury, Venus, Earth, Mars, the asteroid belt, all of it would be inside the star. Everything inside, all the inner planets, would be vaporized, consumed by a star so massive that light itself takes about 7 hours just to travel from one side to the other. Light, moving at 186,000 miles per second, needs that long to cross this star. Think about that. Light can circle the Earth multiple times in a single second, but it needs the better part of a workday to travel across UY Scuti. And yet, even these supergiants are dwarfed by the hypergiants. Stephenson 2-18, possibly the largest known star, has a radius estimated at about 2,150 times that of the Sunday. A single one of these monsters contains more matter than hundreds of thousands of suns combined. If you could somehow gather up hundreds of thousands of sun-sized stars and merge them together, you'd get something like Stephenson 2-18. The volume of this star is so vast that you could fit billions of Earths inside it with room to spare. But here's the cosmic irony. These massive giants live fast and die young. It's like the rock stars of the stellar world. They shine bright, they blaze hot, and they burn out quickly. While our Sun will glow for about 10 billion years total, a hypergiant like Stephenson 2-18 will consume its fuel in just a few million years. Maybe 3 million, maybe 5 million. A blink of an eye in cosmic terms. The bigger the star, the shorter its life, because massive stars operate so intensely that they consume their nuclear fuel at prodigious rates. These massive stars are essentially self-destructive. Their own gravity compresses them so intensely that fusion in their cores happens at rates millions of times faster than in the Sunday. They're converting thousands of tons of matter into energy every second, far more than the Sunday. They shine with the light of millions of suns. But this means they run out of fuel incredibly quickly. A star 100 times more massive than the Sun might only live for a few million years before it explodes as a supernova. It's born, it shines brightly for a cosmically brief moment, and then it dies violently. Now, let's flip that around and look at the other end of the scale. Red dwarfs, the smallest true stars, can have masses as low as about 7.5% that of the Sun. These tiny furnaces burn so slowly, so efficiently, that they'll outlive every other type of star by orders of magnitude. A red dwarf star can shine for trillions of years, not billions, trillions. That's longer than the current age of the universe by a factor of 100 or more. The universe is 13.8 billion years old. Some red dwarfs will live for 10 trillion years or more. In fact, not a single red dwarf that has ever formed has yet died of old age. The universe simply isn't old enough yet. Every red dwarf that ignited fusion in the early universe is still shining today. Every single one. And they'll continue shining long after stars like our sun have burned out and died. These will be the last stars shining when everything else has burned out, lonely embers in a cosmos that has grown cold and dark. Imagine that. Trillions of years from now, when the universe is ancient beyond comprehension, when galaxies have drifted so far apart that each one exists in isolation, when most stars have burned out and died, red dwarfs will still be there, still fusing hydrogen, still shining, providing the only light in an otherwise dark universe. They'll be cosmic lighthouses in an ocean of darkness, the last remnants of the age of stars. But wait, there's something even stranger than red dwarfs. Brown dwarfs, sometimes called failed stars, are objects that never quite made it. They have masses between about 13 and 80 times that of Jupiter. That's big, enormous, even by planetary standards, but not quite big enough to be a true star. They're enough to fuse deuterium, a heavy isotope of hydrogen, but not enough to sustain regular hydrogen fusion like true stars. They're cosmic might-have-beens, objects caught in the liminal space between planets and stars. They glow with heat from their formation and from the limited fusion they can manage, but slowly cool and fade over billions of years. These objects are the ghosts of stars that never lived. And brown dwarfs are actually quite common. There might be billions of them floating through our galaxy, dark objects that are hard to detect because they emit so little light. Neither stars nor planets, but something in between. These are failed attempts at stellar ignition that never quite reached the critical mass needed to sustain fusion. And here's where the stellar classification system gets beautifully weird. Astronomers categorize stars using a sequence of letters. These represent different temperature ranges, with O stars being the hottest and M stars the coolest. The Sun is a G-type star, sitting comfortably in the middle. But the temperature differences are staggering. O-type stars have surface temperatures over 30,000 Kelvin. For reference, that's about 54,000 degrees Fahrenheit. They glow blue-white with such intensity that most of their light is emitted as ultraviolet radiation. If you could somehow get close to an O-type star, you wouldn't see much visible light. Most of its energy would be in wavelengths your eyes can't detect, but that would fry you with radiation in seconds. M-type red dwarfs, on the other hand, have surface temperatures as low as 2,500 Kelvin, about 4,000 degrees Fahrenheit. They're so cool, relatively speaking, that they glow deep red, barely visible compared to their hotter cousins. If you replaced the Sun with a red dwarf, Earth would freeze. We'd be too far away to receive enough energy to maintain liquid water. The habitable zone around a red dwarf is much closer to the star, but temperature is just one variable in the cosmic equation. Stars also vary enormously in luminosity, the total amount of energy they radiate. Our Sun outputs about 4 times 10 to the 26th watts of power. That's a 4 followed by 26 zeros. 400 trillion watts. That's more energy in 1 second than human civilization has used in its entire history. Every second, the Sun outputs more energy than all the power plants, all the engines, all the fires, everything humanity has ever burned or used, combined over all of human history. And yet there are stars that make the Sun look dim. R13601, one of the most luminous stars we've ever discovered, radiates energy at a rate several million times greater than the Sunday If you replace the Sun with R13601, Earth would be instantly vaporized, despite being 93 million miles away. The sheer intensity of radiation would superheat our planet's surface to thousands of degrees within hours. Our atmosphere would be stripped away. The oceans would boil off and evaporate into space. The crust would melt. Within a day, Earth would be reduced to a glowing ball of molten rock, and shortly after that, even the rock would evaporate. Nothing would remain. So we have this incredible diversity. Stars ranging from dim red embers, barely glowing in the cosmic darkness, to blue hypergiants that burn with such fury they'll explode in just a few million years. From cool stars where you could theoretically stand on the surface without instantly vaporizing, to monsters so hot that atoms on their surface are being ripped apart by extreme radiation. The range is staggering. The coolest stars are cooler than some ovens. The hottest stars are hotter than anything we can create on Earth. Hotter than nuclear bomb explosions. Hot enough to tear apart matter itself. But here's the question that should be keeping you up at night. Where do stars come from? How does the universe create these nuclear furnaces in the first place? What process can take a cloud of cold gas floating in space and transform it into a ball of nuclear fire? The answer is going to blow your mind, because it involves physics that seems almost magical, processes that take millions of years, and transformations so extreme that they defy imagination. Let's travel to a stellar nursery, a place where stars are being born right now. Picture an enormous cloud of gas and dust floating in the void of space. We're talking about clouds that can be hundreds of light years across. Hundreds of light years. Remember? A light year is about 6 trillion miles. So we're talking about clouds that are hundreds of trillions of miles across, containing enough matter to make millions of stars. These molecular clouds are among the largest structures that can hold together under their own gravity. They're cold, just a few degrees above absolute zero, maybe 10 or 20 degrees Kelvin. That's about minus 440 degrees Fahrenheit. Colder than anything you can imagine. Colder than anywhere on Earth. Colder than the depths of space far from any star. They're dark, blocking the light from stars behind them. When you look at certain parts of the Milky Way and see dark patches where there seem to be no stars, you're often looking at these molecular clouds, dark nebulae blocking the light from stars on the far side. And they're incredibly sparse, with density lower than the best vacuum we can create on Earth. If you were inside one of these clouds, you might find a few thousand atoms per cubic centimeter. That sounds like a lot, but compare it to Earth's atmosphere, which has about 100 billion trillion atoms per cubic centimeter. These clouds are a better vacuum than anything we can create in our most advanced laboratories. And yet, from these tenuous wisps of cosmic gas, stars are born. The process begins with a disturbance. Maybe a nearby supernova sends a shock wave rippling through the cloud, compressing the gas. Maybe two galaxies collide, smashing their gas clouds together and compressing the material between them. Maybe the cloud just becomes so massive, accumulating so much material, that its own gravity becomes unstable and it starts to collapse under its own weight. Whatever the trigger, parts of the cloud begin to collapse. As gas falls inward under gravity, it heats up. This seems counterintuitive at first. How does something falling together get hotter? Shouldn't it get colder as it compresses? But it's basic physics. Gravitational potential energy converts to kinetic energy. And kinetic energy in a gas means temperature. The gas particles are moving faster, colliding more frequently, transferring more energy with each collision. Temperature is just a measure of particle motion. And collapsing gas moves faster. The collapsing region forms what astronomers call a protostar, a hot core surrounded by a disk of swirling gas and dust. But here's where it gets violent. As more material falls onto the protostar, powerful magnetic fields begin to form. These fields channel some of the infalling material into jets that blast out from the poles at tremendous speeds. We're talking about material moving at hundreds of miles per second, sometimes thousands of miles per second. These jets can extend for light years, carrying away excess angular momentum and allowing more material to fall onto the growing protostar. The developing star is hidden behind a cocoon of dust, invisible to optical telescopes, but glowing brightly in infrared light from the heat of its formation. If you could see in infrared, these protostars would be brilliant beacons, glowing red-hot as they accumulate mass and heat up. The dust around them absorbs the visible light and re-emits it as infrared radiation, creating spectacular infrared nebulae. This process takes time. For a star like our Sun, the collapse from initial disturbance to a fully formed star takes about 50 million years. 50 million years of slow gravitational collapse, of material falling inward, of the core getting hotter and denser. For more massive stars, it can happen much faster, perhaps just 100,000 years. They collapse so rapidly under their own intense gravity that they reach fusion temperatures quickly. For smaller stars, it can take over 100 million years. More than 100 million years of slowly, gradually accumulating mass and heating up. But eventually, something extraordinary happens. The core of the protostar becomes so hot and so dense that hydrogen nuclei begin to fuse into helium. The temperature reaches about 10 million degrees Celsius. The pressure becomes enormous. And suddenly, hydrogen nuclei that have been bouncing off each other for millions of years start merging together. Nuclear fusion ignites. The star is born. The moment of ignition is spectacular. The sudden release of energy halts the gravitational collapse. The star reaches what astronomers call hydrostatic equilibrium, a perfect balance between the inward pull of gravity trying to crush the star and the outward pressure of fusion trying to blow it apart. This balance is so precise, so perfectly maintained, that it can last for billions of years. The star has found its equilibrium, its place in the cosmic order. It will remain stable, fusing hydrogen into helium in its core for the vast majority of its life. And this is the remarkable thing about stars. They're self-regulating. If the nuclear reaction increases slightly, the star heats up, expands, and the expansion cools the core, which decreases the reaction rate. If the process slows down, the star contracts, heats up, and fusion increases again. It's a cosmic thermostat, automatically adjusting to maintain stability. This is why stars can shine steadily for billions of years without burning out or exploding. They've found a perfect balance, an equilibrium that's stable over timescales longer than the existence of complex life on Earth. But not all stars are born alone. In fact, most stars form in groups. When a massive molecular cloud collapses, it doesn't usually form just one star. The cloud is turbulent, with eddies and currents and density variations throughout. It fragments into hundreds or thousands of separate collapse regions, each forming its own star or system of stars. The result is a star cluster, a group of stars born from the same cloud at roughly the same time, all siblings in a cosmic sense. These clusters can be spectacular. The Pleiades, visible to the naked eye on a clear night, is a young cluster containing over 1,000 stars, all born from the same molecular cloud. They're all roughly the same age, about 100 million years old. Young, energetic stars still surrounded by remnants of their birth cloud. The Omega Centauri cluster contains about 10 million stars packed into a sphere only 150 light-years across. That's an enormous density of stars. If we lived in Omega Centauri, the night sky would contain thousands of stars brighter than Venus. The sky would never truly be dark. But star formation doesn't just create individual stars or clusters. It creates entire stellar populations that shape the evolution of galaxies. In regions of intense star formation, thousands of massive stars can form within a relatively small volume of space. These stars live fast and die young, exploding as supernovae within just a few million years. And those supernovae don't just mark the deaths of stars, they trigger new star formation. The shock waves from these explosions trigger more star formation, compressing nearby gas clouds and causing them to collapse. This creates a cascade of stellar birth and death that can reshape entire galaxies. We see this in starburst galaxies, where stars are forming at rates hundreds or even thousands of times faster than in the Milky Way. Entire regions of these galaxies glow brilliantly with the light of newborn stars. It's star formation on an industrial scale, churning out new stars at prodigious rates. And here's something that should blow your mind. The process of star formation actually limits itself. Massive stars produce intense radiation and powerful stellar winds that blow away the remaining gas in their birth cloud. The radiation pressure and stellar winds from hot, massive stars can disperse an entire molecular cloud, preventing further star formation. This feedback prevents too many stars from forming and stops the galaxy from converting all its gas into stars too quickly. Without this self-regulation, galaxies would have exhausted their gas supplies billions of years ago, and no new stars would form anywhere in the universe today. Galaxies would have used up all their gas in one massive burst of star formation early in their history, and then gone dark as all the stars aged and died. The fact that star formation continues, that we see new stars being born in our galaxy and others, is due to this delicate balance between the collapse of gas clouds and the disruption caused by the stars themselves. But let's zoom back in to a single star and explore what's really happening inside these cosmic furnaces. Let me take you on an imaginary journey from the surface of the sun down to its core. Strap in, because it's going to get weird. At the surface, the photosphere, temperatures are a relatively cool 5,500 degrees Celsius. This is where the light we see comes from, where photons finally escape after their long journey from the core. But this surface is anything but calm. It's covered in granules, convection cells, where hot plasma rises and cooler plasma sinks. Each cell is about 1,000 kilometers across, roughly the size of a country like France or Texas. The entire surface is a roiling, churning mass of plasma, with hot material constantly rising and cool material sinking. And superimposed on this granulation are sunspots, regions of intense magnetic activity, where the magnetic field is so strong it suppresses convection and cools the surface. Sunspots can be larger than Earth itself. The largest sunspots are big enough to swallow Earth several times over. As you descend below the photosphere, you pass through the convection zone, a region 200,000 kilometers thick, where energy is transported by the physical motion of plasma. Hot material rises from below, reaches the surface, cools, and sinks back down. This churning motion takes about a month to complete one full cycle. It's like a giant boiling pot, but instead of water, it's ionized plasma at temperatures of millions of degrees. Below that, you enter the radiative zone, where energy moves through the plasma by photons bouncing from atom to atom. Here, instead of convection, energy travels as radiation. Photons are constantly being absorbed and re-emitted by atoms, taking a random walk through the dense plasma. A single photon can take over 100,000 years to random walk its way from the core to the edge of the radiative zone, even though it's always traveling at the speed of light. 100,000 years to travel a distance that light could cross in a few seconds if it weren't constantly being absorbed and re-emitted. This is why, if fusion in the sun's core were to suddenly stop right now, we wouldn't know for over 100,000 years. The photons produced by the last fusion reactions would still be bouncing around inside the sun for millennia. The sun would continue shining, unaware that its core had gone dark, until those last photons finally made their way to the surface. Finally, you reach the core, the heart of the star, where the magic happens. The core of the sun is about 15 million degrees Celsius, and the pressure is about 250 billion times Earth's atmospheric pressure. Try to wrap your head around that. 250 billion times the pressure you're feeling right now. Under these extreme conditions, matter doesn't behave the way you're used to. Electrons are stripped from atom. Nuclei are moving at incredible speeds, colliding with tremendous force. And it's here that hydrogen nuclei are moving so fast and colliding so violently that they overcome their electromagnetic repulsion and fuse together. The primary mechanism in sun-like stars is called the proton-proton chain reaction. It's a multi-step process. First, two hydrogen nuclei, two protons, fuse to form a deuterium nucleus, one proton and one neutron. This releases a positron and a neutrino. Then the deuterium fuses with another proton to form helium-3, two protons and one neutron. Finally, two helium-3 nuclei fuse to form helium-4 and release two protons. The net result is that four hydrogen nuclei combine to create one helium nucleus. The helium nucleus has slightly less mass than the four hydrogens that formed it. Where did that missing mass go? It's been converted to energy according to E equals mc squared. That missing mass becomes the light and heat that we feel from the sunday. But here's what's truly remarkable about stellar fusion. It shouldn't work. At the temperatures and pressures in the stellar core, hydrogen nuclei still don't have quite enough energy to overcome the electromagnetic repulsion between their positive charges. Classically, they shouldn't be able to get close enough to fuse. The electromagnetic repulsion should keep them apart. But quantum mechanics comes to the rescue with a phenomenon called quantum tunneling. In quantum mechanics, particles don't have definite positions. They exist as probability waves, and there's a small but non-zero probability that a particle can appear on the other side of a barrier it doesn't have enough energy to overcome classically. The hydrogen nuclei have a small probability of tunneling through the electromagnetic barrier, allowing fusion to occur at lower energies than classical physics would allow. Without quantum tunneling, stars couldn't exist. The temperatures and pressures wouldn't be high enough for fusion. And without stars, there would be no heavy elements, no planets, no life. Quantum mechanics isn't just some abstract theory. It's the reason you exist. The energy released by fusion in the core creates an outward pressure that balances the inward gravitational force. This balance is so precise that if the fusion rate increases even slightly, the star heats up, expands, and the expansion cools the core, which decreases the fusion rate. It's negative feedback. If the fusion rate decreases, the star contracts, heats up, and fusion increases. Positive feedback that restores equilibrium. It's a cosmic thermostat, automatically maintaining stable conditions for billions of years. This is why stars spend most of their lives on what astronomers call the main sequence, a stable period where they're fusing hydrogen into helium in their cores. Our Sun is about halfway through this phase. It's been fusing hydrogen for 4.6 billion years and will continue for about another 5 billion years. But not all stars age at the same rate. A massive O-type star might spend only a few million years in this stable state before exhausting its core hydrogen. A tiny red dwarf might remain stable for several trillion years, outlasting the current age of the universe by factors of hundreds. But eventually, inevitably, every star runs out of hydrogen in its core. And that's when things get really interesting, because what happens next depends entirely on the star's mass, and the variations are spectacular. The death of a star can be gentle or violent, quick or slow, quiet or explosively bright. Let's start with stars like our Sun, middle-mass stars that will die relatively peacefully. When the Sun exhausts the hydrogen in its core, fusion will stop, and the core will begin to contract under its own gravity. No longer supported by fusion pressure, gravity takes over. This contraction heats the core, and here's the thing. The core gets hotter even though fusion has stopped. Gravitational contraction converts potential energy to thermal energy, heating the core to temperatures even higher than before. The temperature in the region surrounding the core becomes hot enough for hydrogen fusion to ignite there. The star now fuses hydrogen in a shell around an inert helium core. It's shifted from core fusion to shell fusion, and this shell fusion produces more energy than core fusion did, much more. The additional energy causes the star's outer layers to expand dramatically. The Sun will swell to become a red giant, expanding to perhaps 50 or 100 times its current size. Its surface will eventually reach beyond the orbit of Mars. Earth will be engulfed, swallowed by the expanding stellar atmosphere. Our planet will spiral inward through the Sun's outer layers, experiencing temperatures of thousands of degrees. The atmosphere will be stripped away first. Then, the oceans will boil off and evaporate. The crust will melt. Eventually, Earth will be vaporized entirely, its atoms scattered throughout the Sun's atmosphere. Everything we've ever built, every person who's ever lived, every species that's ever evolved, all of it will be reduced to individual atoms floating in a sea of hydrogen and helium. But from a distance, the red giant Sun will actually appear fainter than it does now because the same amount of energy output is spread over a much larger surface area. The surface temperature will drop to about 3000 Kelvin, giving the star its characteristic red color. It's called a red giant because it's red and giant. Simple enough. Inside the red giant, the helium core continues to contract and heat up. It's getting smaller and denser and hotter. Eventually, if the star is massive enough, and fortunately for stars like the Sun, they are just barely massive enough, the core reaches about 100 million degrees. 100 million degrees. And at that temperature, helium fusion ignites. 3 helium nuclei combine to form carbon through a process called the triple alpha process. It's called that because helium nuclei are also called alpha particles. 3 alphas fuse to make carbon. This happens suddenly in an event called the helium flash, a runaway fusion reaction that releases as much energy in a few seconds as the entire Milky Way galaxy produces in the same time. Think about that. For a few seconds, the core of a dying star is brighter than 100 billion stars combined. For stars like the Sun, the helium flash is absorbed by the outer layers and doesn't destroy the star. The enormous energy release is cushioned by the thick envelope of gas surrounding the core. But it's a violent transition nonetheless. The star, essentially explodes on the inside, though the explosion is contained and doesn't blow the star apart. The star now enters a new stable phase, fusing helium in its core and hydrogen in a shell around it. It's running two fusion reactions simultaneously. But this phase is much shorter than the main sequence. Our Sun will fuse helium for only about 100 million years. Compare that to the 10 billion years it spends fusing hydrogen. Helium fusion is less efficient and releases less energy per reaction, so the core has to fuse more fuel faster to maintain equilibrium. When the helium is exhausted, the core will contract again, and helium fusion will move to a shell around a carbon-oxygen core. Now the star is running 3 layers: a carbon-oxygen core that's not fusing, a shell of helium fusion around that, and a shell of hydrogen fusion around that. The star will become even larger and more unstable, pulsating irregularly as thermal pulses send shock waves through the stellar atmosphere. These thermal pulses happen when the helium shell fusion becomes unstable. Every few thousand years, the helium shell will suddenly increase its fusion rate, producing a surge of energy that causes the star to brighten and expand. Then the shell cools, fusion decreases, and the star contracts again. It's like a beating heart, pulsing with periods of thousands of years instead of fractions of a second. Finally, after several of these pulses, the star will shed its outer layers in a series of gentle puffs, creating a planetary nebula, one of the most beautiful structures in astronomy. The expelled gas glows with brilliant colors as it's illuminated by the hot core of the dying star. You've probably seen pictures of these: the Ring Nebula, the Helix Nebula, the Cat's Eye Nebula. These are all planetary nebulae, the shed atmospheres of dying sun-like stars. That core, no longer producing energy through fusion, will cool and fade, becoming a white dwarf. An object about the size of Earth, but with a mass comparable to the Sunday, the entire mass of the Sun, compressed into a sphere the size of our planet. The density is so extreme that a teaspoon of white dwarf material would weigh about 15 tons on Earth. A single teaspoon would weigh as much as 2 elephants. White dwarfs are held up not by fusion or thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect. The Pauli exclusion principle states that no 2 electrons can occupy the same quantum state. When you try to compress matter, you're trying to force electrons into the same state, and quantum mechanics says no. This creates a pressure that has nothing to do with temperature. Even a cold white dwarf is supported by this quantum pressure. As the white dwarf cools, it will fade over trillions of years, eventually becoming a black dwarf, a cold, dark stellar remnant. However, the universe is not yet old enough for any black dwarfs to have formed. The cooling time for a white dwarf is longer than the current age of the universe. Every white dwarf that exists is still glowing with the remnant heat of its stellar past. In a sense, they're still alive, still warm from their formation. But that's the fate of stars, like the Sunday. For more massive stars, the story is much more dramatic, much more violent, much more spectacular, and much more important for creating the elements that make up everything around you. Stars with masses greater than about 8 times the Sun have enough gravitational pressure to fuse elements heavier than carbon. After helium burning creates a carbon-oxygen core, the story doesn't end there. The core contracts and heats up further. When the core reaches about 600 million degrees, carbon can fuse. Carbon fuses into neon and magnesium. Then the carbon is exhausted and the core contracts and heats up again. At about 1 billion degrees, neon starts fusing into oxygen and magnesium. Then neon is exhausted. The core contracts and heats up. At about 2 billion degrees, oxygen fuses into silicon and sulfur. Then oxygen is exhausted. The core contracts and heats up at about 3 billion degrees. Silicon fuses, and silicon fusion produces iron. Iron is the end of the line, the most stable nucleus in nature. You can't get energy from fusing iron. In fact, fusing iron requires energy. It's endothermic rather than exothermic. So when the core becomes pure iron, fusion stops completely. Each stage of fusion happens faster than the one before. The star might fuse hydrogen for millions of years, helium for hundreds of thousands of years, carbon for a few hundred years, neon for about a year, oxygen for a few months, and silicon for a few days. The silicon fusion stage, the final stage of fusion before the core becomes iron, lasts less than a week. In less than a week, the core of a massive star converts silicon into iron and seals its fate. The star becomes like a cosmic onion, with layers of different elements undergoing fusion at different depths. The core is iron, surrounded by a shell of silicon fusion, then oxygen fusion, then neon fusion, then carbon fusion, then helium fusion, then hydrogen fusion at the outermost fusion shell. The star looks stable from the outside, shining brightly, giving no outward sign that anything is wrong. But internally, it's a ticking time bomb. Once the core becomes iron, the clock is ticking. And the countdown is measured in seconds, not years. Here's why. Iron is special. It's the most tightly bound nucleus in the periodic table. Every fusion reaction before iron released energy. But fusing iron doesn't release energy. It requires energy. When the core becomes pure iron, fusion stops completely. And without the outward pressure from fusion, nothing can support the core against gravity. The iron core might be 100 times more massive than Earth, but it's only about the size of Earth. The density is already enormous, but gravity wants to compress it further. And then it happens. The core collapses. In less than a second, maybe a quarter of a second, the iron core, roughly the size of Earth, collapses to an object maybe 20 kilometers across. From the size of Earth to the size of a city in less time than it takes to blink. The density becomes so extreme that protons and electrons are forced together to form neutrons. It's inverse beta decay on a massive scale. The core becomes a neutron star, a ball of neutrons so dense that a teaspoon of it would weigh as much as a mountain, as much as Mount Everest. The collapse happens so fast that the infalling material overshoots equilibrium. It bounces, the core compresses, stops, and rebounds. This sends a shock wave racing outward through the star at tremendous speed. The shock wave carries with it more energy than the star produced in its entire lifetime. Think about that. The star has been fusing elements for millions of years, releasing enormous amounts of energy every second. The supernova explosion releases more energy than all of that combined. It tears through the outer layers at a significant fraction of the speed of light. What was once a massive star becomes a supernova. An explosion so bright it can briefly outshine an entire galaxy of hundreds of billions of stars. For a few weeks, this single exploding star is brighter than 100 billion normal stars. The supernova can remain visible for weeks or months, slowly fading as the ejected material expands and cools. The material expelled by the supernova is moving at tens of thousands of miles per second. It crashes into the surrounding interstellar medium, creating a supernova remnant, an expanding shell of hot gas that can be light years across. The Crab Nebula is a supernova remnant from a star that exploded in the year 1054. Chinese astronomers recorded it. They saw a guest star so bright it was visible during the day for several weeks. That was a star, about 6,000 light-years away, exploding with such violence that it was visible in broad daylight from Earth. But the supernova does something even more remarkable than just being spectacularly bright. Remember how I said fusion stops at iron? Well, during the supernova explosion, conditions become so extreme that elements heavier than iron can be formed through rapid neutron capture. In the core collapse and the subsequent explosion, neutrons are produced in enormous quantities. These neutrons can be captured by atomic nuclei, which then beta decay into heavier elements. Gold, platinum, uranium, every element heavier than iron in the universe was created in supernova explosions or in even more exotic events like neutron star collisions. Every single atom of gold in existence was created in a supernova or neutron star merger. There's no other way to make it. You can't make gold in a laboratory, not in any meaningful quantity, because you'd need the conditions of a supernova. Every gold atom in your wedding ring, every platinum atom in a catalytic converter, every uranium atom in nuclear reactors, all of it came from the death throes of massive stars. You are wearing stellar corpses. Literally, your jewelry is made from atoms forged in explosions so violent they outshine galaxies. The metal in your car, the uranium in power plants, the gold in electronics, all of it comes from stars that died billions of years ago. Your body contains atoms forged in supernovae that exploded billions of years ago, long before our solar system existed. The iron in your blood, essential for carrying oxygen, the calcium in your bones, providing structure, the oxygen you breathe, necessary for life. All of it was created inside stars and scattered into space when those stars died. You are made of atoms that have been through multiple stellar cycles, created in ancient stars, scattered by supernovae, collected into new molecular clouds, incorporated into the sun and planets, and eventually ending up in you. But we're not done with supernovae yet, because what's left behind after the explosion is arguably even stranger than the explosion itself. The neutron star core is one of the most extreme objects in the universe. A typical neutron star has about 1.4 times the mass of the Sun compressed into a sphere only about 20 kilometers in diameter. 20 kilometers. That's about the size of Manhattan. Imagine compressing the entire Sun, which is over 1 million kilometers across, into a sphere the size of a city. The density is around 1 billion tons per cubic centimeter. 1 billion tons. In a space the size of a sugar cube, the surface gravity is about 200 billion times stronger than Earth's gravity. If you could somehow stand on a neutron star, which you absolutely couldn't, you would weigh as much as Mount Everest weighs on Earth. Your body would be crushed to a thickness measured in atoms. You'd be smeared across the surface in a layer less than a millimeter thick. The magnetic fields of neutron stars are the strongest in the universe, typically about 1 trillion times stronger than Earth's magnetic field. 1 trillion times. If a neutron star with an average magnetic field passed within 100,000 miles of Earth, it would wipe all the magnetic data from every device on the planet. Every hard drive erased. Every credit card demagnetized. Some neutron stars, called magnetars, have fields 1,000 times stronger still, 1 trillion times 1,000. These magnetic fields are so powerful they can rip apart atoms. The magnetic force overcomes electromagnetic forces holding atoms together. Atoms become elongated, stretched into thin cigar shapes aligned with the magnetic field. Matter stops behaving like matter and becomes something else, something we don't fully understand. If a magnetar appeared just 1,000 kilometers from Earth, the distance from New York to Chicago, it would strip the electrons from every atom in your body. You wouldn't die from the experience in any conventional sense. You'd simply cease to be recognizable as matter. Your atoms would be torn apart. The electrons would be ripped away. You'd be ionized at the atomic level. It's not death, it's disintegration. Many neutron stars spin at extraordinary rates. Pulsars, neutron stars that emit beams of radiation from their magnetic poles, can rotate hundreds of times per second. The fastest known pulsar spins 716 times per second. 716 rotations every single. Imagine an object more massive than the sun, compressed to the size of a city, spinning so fast that its surface is moving at a significant fraction of the speed of light. At the equator of this pulsar, the surface is moving at about 24% of light speed, 75 million meters per second. If you were somehow standing on that surface, you'd experience acceleration forces billions of times stronger than Earth's gravity. The spin is so fast that relativistic effects become significant. Time dilation, length contraction, all the weird predictions of special relativity become important. The physics involved is so extreme that neutron stars are essentially the largest atomic nuclei in the universe. They're not made of atoms, they're made of neutrons packed together at nuclear density. It's like one giant nucleus, held together by gravity rather than the strong nuclear force. Some physicists call them neutronium, matter in a state that can't exist anywhere else in the universe. The only place neutronium can exist is in neutron stars, where gravity is strong enough to overcome the neutron degeneracy pressure that would otherwise cause the material to explode. But neutron stars aren't the strangest stellar remnants. For the most massive stars, stars above about 25 times the mass of the Sun, even neutron degeneracy pressure isn't enough to halt the core collapse. The core continues, contracting past the neutron star stage. Gravity is too strong, the compression continues, and then something happens that defies every intuition you have about reality. The escape velocity at the surface exceeds the speed of light. Think about what that means. The escape velocity, the speed you'd need to achieve to escape the gravitational pull, becomes greater than the fastest speed possible in the universe. Nothing can escape. Not matter, not light, not information. Space itself becomes so warped that all trajectories lead inward. Forward in time means falling toward the center. The object becomes a black hole. Black holes are regions of space-time where gravity has become so strong that nothing, not even light, can escape. The boundary of no return is called the event horizon, and once you cross it, there's no coming back. Not because you can't move fast enough, but because all possible directions forward in time lead toward the center. Trying to escape a black hole after crossing the event horizon is as futile as trying to travel backward in time. It's not just difficult, it's literally impossible. The structure of space-time itself prevents it. At the center of the black hole, according to general relativity, lies a singularity, a point of infinite density where the known laws of physics break down. But here's what should mess with your head. We don't actually know what's at the center. Our best theories of physics can't handle infinities. When you get an infinity in physics, it usually means your theory has broken down, that you're missing something important. Most physicists suspect that quantum gravity effects, which we don't yet understand, prevent the formation of true singularities. The center might be a Planck scale structure, an object about 10 to the negative 35 meters across. That's a decimal point, followed by 34 zeros, and then a 1. Unimaginably small. Or it might be a region where space-time itself becomes quantum and grainy, pixelated like a digital image when you zoom in too far. Or it might be something we don't have the conceptual framework to describe yet, something so far outside our experience that we lack even the vocabulary to discuss it. Black holes come in different sizes. Stellar black holes, formed from supernova explosions, typically have masses between about 5 and 100 times the Sunday. Their event horizons are only a few kilometers to a few hundred kilometers across. A black hole with 10 times the mass of the Sun would have an event horizon only about 60 kilometers in diameter. You could fit it inside a large city, but inside that city-sized region, space-time is so warped that nothing can escape. But there are much larger black holes lurking at the centers of galaxies. Supermassive black holes have masses millions or billions of times the Sunday. The black hole at the center of our Milky Way, Sagittarius, a star, has a mass about 4 million times that of the Sunday. Its event horizon is about 24 million kilometers in diameter. That's about 60 times the distance from Earth to the Moon. The largest black holes we've discovered have masses over 60 billion solar masses. 60 billion times the mass of the Sunday. Their event horizons would encompass the entire solar system several times over. How these supermassive black holes formed is still a mystery. They're so massive that they couldn't have grown from stellar black holes alone. There hasn't been enough time since the Big Bang. Even if a stellar black hole ate continuously for 13.8 billion years, it couldn't reach billions of solar masses. The feeding process is limited by radiation pressure. As material falls in, it heats up and emits radiation, which pushes other material away. Some might have formed from direct collapse of massive clouds of gas in the early universe. Instead of fragmenting into stars, the entire cloud collapsed directly into a black hole. Others might have grown through mergers of smaller black holes with multiple stellar mass or intermediate mass black holes combining over billions of years. We've actually detected the gravitational waves from such mergers, ripples in spacetime itself produced when two black holes spiral together and merge into one. The detection of gravitational waves is one of the most remarkable scientific achievements of recent decades. When two black holes merge, they release more energy in a fraction of a second than all the stars in the observable universe combined. But that energy isn't released as light. It's released as gravitational waves, distortions in spacetime that propagate outward at the speed of light. When these waves pass through Earth, they stretch and squeeze space itself by amounts smaller than the width of a proton, and we can detect them. We've built instruments sensitive enough to measure distortions smaller than atomic nuclei. But black holes, despite being stellar corpses, despite being the end products of stellar evolution, play a crucial role in the life of galaxies. The supermassive black holes at galactic centers regulate star formation through their influence on surrounding gas. When material falls into these black holes, it forms an accretion disk, a swirling maelstrom of superheated matter spiraling inward. The material in this disk is moving at tremendous speeds, sometimes approaching the speed of light. Friction in the disk heats the material to millions of degrees, causing it to emit powerful radiation, often more energy than all the stars in the galaxy combined. Some of this material doesn't fall into the black hole. It's channeled by magnetic fields into relativistic jets that blast out from the poles at nearly the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the galaxy itself. They drill through intergalactic space, pumping enormous amounts of energy into the surrounding medium. These jets and the radiation from the accretion disk can blow away gas from the galaxy, shutting down star formation. The radiation and jets heat the gas to such high temperatures that it can't collapse to form stars. This feedback is why the most massive galaxies have relatively few young stars. Their central black holes have become so powerful that they've ejected most of the star-forming gas. The galaxies are essentially sterilized, unable to form new stars because the black hole has removed the raw material. Without this regulation, galaxies would form stars too quickly and exhaust their gas supplies, changing the entire character of the universe. There'd be a brief period of intense star formation, then nothing. Galaxies would go dark as all the stars aged and died and no new stars formed to replace them. The fact that galaxies continue to form stars at a steady rate over billions of years is due to this balance between gas cooling and collapsing to form stars and black holes heating and ejecting that gas. Now, let's step back and consider something profound. Something that should fundamentally change how you see yourself. Every element in your body, except hydrogen, was created inside stars. Let me say that again. Every single atom in your body, heavier than hydrogen, was created inside a star. The hydrogen in your body, about 10% of your atoms by number, about 60% by mass since hydrogen is so light, was created in the Big Bang. But everything else, the carbon, the nitrogen, the oxygen, the phosphorus, the calcium, the iron, all of it was synthesized in the nuclear furnaces of stars over billions of years. You are literally made of star stuff. This isn't a metaphor or poetic language, it's scientific fact. It's not an exaggeration or simplification for dramatic effect. It's the literal truth. The atoms that compose you were forged in stellar cores and scattered into space by stellar winds, planetary nebulae, and supernova explosions. They drifted through the cosmos for millions or billions of years, eventually collecting into the molecular cloud that formed our solar system. They were incorporated into the disk of material around the young sun, accreting into the planets, and eventually finding their way into the Earth. Through geological processes over billions of years, those atoms moved from the interior of the planet to the surface. Through chemical evolution, they became part of organic molecules. And through billions of years of biological history, those stellar atoms were assembled into the arrangement that is you. Every time you breathe, you're inhaling atoms that were once inside multiple different stars. Oxygen atoms created in massive stars that exploded as supernovae billions of years ago. Nitrogen atoms forged in intermediate mass stars and scattered by planetary nebulae. Carbon atoms from various stellar sources. Every breath you take contains stardust. Every time your heart beats, it's powered by energy extracted from molecules built from stellar debris. The glucose that fuels your cells is made from carbon, hydrogen, and oxygen atoms that came from dead stars. The ATP that stores energy in your body contains phosphorus that was created in supernovae. Your entire metabolism, every chemical reaction in your body, relies on atoms created by nuclear fusion inside stars. Your consciousness itself, your ability to wonder about stars and your place in the cosmos, is the universe's way of understanding itself through structures built from ancient stellar ash. Think about that. You are the universe looking at itself. The atoms in your brain were once inside stars. Those atoms are now arranged in a configuration that can think, that can ponder existence, that can understand where it came from. The cosmos has organized itself in such a way that it can contemplate its own nature. But stars don't just create the elements necessary for life. They also create the conditions necessary for life. Consider that every star is flooding space with light and heat. Planets orbiting at the right distance can have stable temperatures where liquid water exists. This habitable zone, sometimes called the Goldilocks zone, varies with the type of star. Around hot, massive stars, the habitable zone is farther out, maybe several astronomical units from the star. But it's short-lived because the star burns out quickly. Around cool, small stars, The habitable zone is very close in, maybe just a few million miles from the star, but it can remain stable for trillions of years. Red dwarfs will still be shining long after our sun has died, potentially hosting habitable planets for timescales far longer than Earth has been habitable. Our sun is in many ways ideal for life. It's stable, providing consistent energy output over billions of years. The sun's luminosity varies by less than 0.1% over timescales of decades. This stability is crucial. If the sun's output varied significantly, Earth's climate would swing wildly, making long-term biological evolution difficult or impossible. It's metal-rich, meaning the protoplanetary disk contained plenty of heavy elements to form rocky planets. The sun formed from a cloud that had been enriched by previous generations of stars. Without that enrichment, there wouldn't have been enough silicon, magnesium, iron, and other elements to build rocky planets like Earth. It's a single star. Many stars exist in binary or multiple star systems where planetary orbits would be unstable. In a binary system, gravitational perturbations from the two stars can destabilize planetary orbits, ejecting planets from the system or causing their orbits to become highly elliptical. Earth needs a stable, nearly circular orbit to maintain a stable climate. In a binary system, that would be difficult or impossible. It's not too massive, so it will live long enough for complex life to evolve. Life on Earth arose relatively quickly within the first billion years, but complex multicellular life took billions of years to develop. Intelligence took even longer. The sun needs to shine steadily for billions of years to give evolution time to work. More massive stars don't live long enough, and it's not too small, so planets in the habitable zone aren't tidally locked, which would make climate regulation difficult. Around red dwarfs, the habitable zone is so close that planets are likely to be tidally locked, always showing the same face to their star. This could create temperature extremes, with one side perpetually hot and the other perpetually cold. While some climate models suggest such planets could still be habitable, it's more challenging than having a rotating planet with day-night cycles. The sun is also old enough that it formed from gas, enriched by previous generations of stars. The very first stars, called population 3 stars, formed from pure hydrogen and helium. There were no heavy elements yet. Those stars had to live, die, and scatter their enriched ashes into space before stars like the sun could form, with planetary systems capable of supporting life. We exist because multiple generations of stars lived and died before our solar system formed. We're made of recycled stellar material that went through at least 2, probably 3 or more generations of stars before becoming us. This creates a cosmic timeline for life. The universe is 13.8 billion years old. The first stars formed a few hundred million years after the Big Bang, maybe around 200 million years after the beginning. But those were massive, short-lived stars that quickly exploded, seeding the universe with the first heavy elements. Subsequent generations gradually enriched the cosmos with more metals. By the time our solar system formed 4.6 billion years ago, there had been enough stellar processing that rocky planets rich in complex chemistry could form. Life on Earth arose relatively quickly, within the first billion years after Earth's formation. Simple, single-celled life was present by about 3.5 billion years ago, maybe earlier. But complex, multicellular life took billions of years longer. It wasn't until about 600 million years ago that complex animals appeared. Intelligent life capable of understanding stars and building civilizations has existed for only a few million years at most. And technological civilization capable of studying the universe scientifically has existed for only a few thousand years. Really just a few hundred years, if we're talking about modern astronomy and astrophysics. The timeline from the Big Bang to conscious observers is long, but it couldn't have been much shorter. The universe needed time to create and distribute the elements, billions of years of stellar processing. It needed time for planetary systems to form from those enriched materials, millions of years of accretion. It needed time for those planets to become stable, billions of years for Earth's climate to stabilize, and for the crust to cool, and for liquid water to become permanently established. And it needed time for evolution to work its slow magic, billions of years to go from simple chemistry to self-replicating molecules to cellular life to multicellular life to intelligence. But here's something that should make you pause. We don't know if we're typical. Earth might be a common outcome of stellar and planetary evolution, in which case the galaxy could be teeming with life. There could be millions or billions of inhabited planets in the Milky Way alone. Or Earth might be extraordinarily rare, a 1 in a trillion accident that required such specific conditions that we might be alone in the observable universe. The answer to this question depends partly on stars and the planets they form. Red dwarf stars are by far the most common type of star, making up about 75% of all stars in the galaxy. 3 out of every 4 stars is a red dwarf. They're stable, long-lived, and numerous. But planets in their habitable zones are so close to the star that they're likely tidally locked, always showing the same face to their sun, like the moon shows one face to Earth. These planets might have one side perpetually scorched and the other permanently frozen, with only a narrow band in between where conditions might support life. Red dwarfs also tend to be very active when young, producing powerful flares that could strip away planetary atmospheres. Young red dwarfs can flare dramatically, increasing their brightness by factors of 10 or more for hours at a time. If a planet is close enough to be in the habitable zone, it's also close enough to receive the full force of these flares. The radiation could strip away the atmosphere, leaving the planet barren. Life might struggle to get started on red dwarf planets. On the other hand, red dwarfs will outlive all other stars, shining for trillions of years. If life can adapt to their conditions, red dwarf systems might ultimately be the best places for long-term habitability. When sun-like stars have burned out and died, and the universe has grown dark and cold, red dwarfs will still be shining, providing energy for any life that manages to persist. The universe of the far future will be dominated by red dwarfs, and whatever life has adapted to their conditions. Larger stars, while spectacular, are probably poor candidates for life. They burn too fast, not giving evolution enough time to produce complexity. Evolution on Earth took billions of years. A massive star might only live for millions of years. There's simply not enough time. Their habitable zones are also unstable. As the star evolves and changes brightness, the habitable zone moves, and they end their lives in violent supernovae that would sterilize any nearby planets. Any life that did manage to develop would be wiped out when the star exploded. The sweet spot for life seems to be stars between about half a solar mass and 1.5 solar masses. These stars are stable, long-lived, and quiet enough to allow planetary environments to remain habitable for billions of years. They're not so massive that they die quickly, and not so small that their planets face extreme challenges. They're the Goldilocks stars, not too big, not too small, but just right. But the question of life around other stars is no longer purely theoretical. In the past few decades, we've discovered thousands of exoplanets, planets orbiting other stars. The first confirmed exoplanet around a sun-like star was discovered in 1995. Just 1995. less than 30 years ago. Before that, we had never confirmed a planet around another star. We strongly suspected they existed, but we had no proof. Today, we know of over 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. And these are just the ones we can detect with current technology. The actual number of planets in the galaxy is estimated to be in the hundreds of billions. There might be more planets than stars. We've found planets of every imaginable type. Hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun, with surface temperatures hot enough to melt metal. Super-Earths, rocky planets, with masses several times our planet, possibly with thick atmospheres and deep oceans. Water worlds that might be entirely covered in liquid water, hundreds of miles deep, with no land masses at all. Rocky planets in the habitable zones of their stars. Temperate worlds where liquid water could exist on the surface and where life might potentially thrive. Some of these planets orbit multiple stars, seeing sunsets with 2 or 3 suns dipping below the horizon, like the iconic scene from Star Wars but real. Others orbit pulsars, bathed in deadly radiation from the neutron star remnants, somehow having survived the supernova that created the pulsar, or having formed from the debris afterward. We found planets around red dwarfs, sun-like stars, and even some more massive stars. The diversity is staggering and suggests that planet formation is a common byproduct of star formation. It's not rare or unusual. It's the norm. Most stars probably have planets. The galaxy is filled with planetary systems. Statistical analyses based on the discoveries so far suggest there might be billions of Earth-sized planets in the habitable zones of stars in our galaxy alone. Billions. If even a tiny fraction of these develop life, even 1% of 1%, the Milky Way could be home to millions or billions of living worlds. And if a fraction of those develop intelligent life, we might have countless civilizations scattered across the galaxy. But the profound silence we detect when we search for signals from other civilizations suggests either that intelligent life is rarer than we hoped, or that civilizations don't last long, maybe destroying themselves shortly after developing technology, or that we're looking in the wrong way, searching for the wrong kind of signals, or at the wrong frequencies, or that they're out there, but we haven't detected them yet because space is so vast and signals are so weak, and we've only been searching for a few decades. This is where stars play another crucial role. If we ever hope to reach other stars, we'll need to overcome the enormous distances involved. The nearest star system, Alpha Centauri, is about 4.37 light-years away. That's about 25 trillion miles. With current technology, it would take tens of thousands of years to get there. Our fastest spacecraft, the Voyager probes launched in 1977, are moving at about 38,000 miles per hour. At that speed, it would take them over 70,000 years to reach Alpha Centauri. If they were headed that direction, which they're not, even traveling at 10% the speed of light, a speed far beyond our current capabilities and requiring technology we don't have, the journey would take over 40 years. You'd need to accelerate to 18,000 miles per second, sustain that speed for over 4 years while coasting through interstellar space, then decelerate at the destination. The energy requirements are enormous. The engineering challenges are immense, and you'd age 40 years during the trip, assuming you could survive the journey. Interstellar travel is limited not by our engineering, but by the fundamental structure of the universe. The vast distances between stars, the cosmic speed limit of the speed of light, the energy requirements of accelerating even small payloads to relativistic speeds. Stars are islands, separated by an ocean of emptiness. And crossing that ocean with current or near-future technology is essentially impossible for human travelers. But perhaps future civilizations will find ways around these limitations. Generation ships that take centuries to reach nearby stars, with multiple generations living and dying during the voyage. Sleeper ships, where crews hibernate for the journey, suspended in some form of stasis for decades or centuries. Or perhaps entirely new physics, like hypothetical warp drives that manipulate space-time itself, allowing faster-than-light travel without actually moving through space faster than light. For now, the stars remain distant lights, tantalizing but unreachable. We can study them, understand them, appreciate them, and learn from them. But we can't yet visit them. We're confined to our solar system, looking outward at the stars that gave us life, wondering if we'll ever be able to reach them. Let's talk about something that will change how you see the night sky forever. When you look at stars, you're literally looking back in time. Light travels at 300,000 kilometers per second. Fast, but not instantaneous. It takes time for light to travel from distant objects to your eyes. The light from the sun takes about 8 minutes to reach Earth. When you watch a sunset, you're seeing the sun as it appeared 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd continue to see it shining, unaware that it was already gone. The nearest star beyond the sun, Proxima Centauri, is 4.24 light-years away. When you see its light, you're seeing it as it was 4.24 years ago. What you're seeing happened over 4 years ago. Sirius, the brightest star in the night sky, is 8.6 light-years away. You're seeing it as it was 8.6 years ago, as it appeared around 2015. Betelgeuse, the red supergiant that forms Orion's shoulder, is about 650 light-years away, though the distance is uncertain. The light you see from Betelgeuse today left the star around the year 1374, during the medieval period on Earth. The light has been traveling across the galaxy for over 6.5 centuries, crossing the vast emptiness of space, while civilizations rose and fell on Earth. Some stars you see with the naked eye are thousands of light-years away. Deneb, one of the brightest stars in the night sky and part of the Summer Triangle, is estimated to be about 2,600 light-years away. You're seeing it as it appeared during the time of ancient Egypt, around 600 BCE. The light left Deneb before the classical Greek civilization, before the Roman Empire, before Christianity. It has been traveling across the galaxy for over 26 centuries. This means the night sky is a time machine. Every star is a window to a different moment in the past. Look in one direction and you see stars as they were a few years ago. Look in another direction and you see stars as they were thousands of years ago. The sky isn't showing you the present state of the galaxy. It's showing you the galaxy's history with different stars representing different chapters, a collage of different time periods, all visible simultaneously. And here's something even stranger. Some of the stars you see might not exist anymore. Betelgeuse, for instance, is nearing the end of its life. It's a red supergiant that could explode as a supernova at any time, astronomically speaking. It might have already exploded, and we're just waiting for the light from that explosion to reach us. We won't know until the light arrives. When Betelgeuse does go supernova, and it will, it's not a question of if, but when. It will be spectacular. For several weeks, it will be brighter than the full moon and visible during the day. It will be by far the brightest object in the night sky besides the moon. You could read by its light. It will be the closest supernova to Earth in recorded history, a once-in-civilization event that anyone alive at the time will remember for the rest of their lives. But that explosion might have already happened 650 years ago, and we're just living in the period before the light arrives. This temporal disconnect becomes even more profound when we look at distant galaxies. The Andromeda Galaxy, the nearest large galaxy to the Milky Way, is about 2.5 million light-years away. When you see Andromeda, you're seeing it as it was 2.5 million years ago, long before humans existed, when our ancestors were still primitive hominids in Africa, barely distinguishable from other apes. The light has been traveling across intergalactic space for longer than our species has existed, longer than the genus Homo has existed. Look deeper into space, and you look further back in time. The Hubble Space Telescope has captured images of galaxies over 13 billion light-years away. We're seeing them as they were less than 1 billion years after the Big Bang, when the universe was young and the first generations of stars were just forming. Those galaxies look different from modern galaxies. More chaotic, more actively forming stars, less organized into the beautiful spiral and elliptical structures we see in nearby galaxies. We're watching cosmic history unfold, seeing how galaxies and stars evolved over billions of years. But there's a fundamental limit to how far back we can see with light. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, it was an opaque plasma where photons couldn't travel freely. They'd be immediately absorbed and re-emitted, scattered by the dense soup of charged particles. Light couldn't propagate through the early universe. That moment, called recombination, is the farthest back we can see with light. The photons from that era, the moment when atoms first formed and light could finally travel freely, have been traveling ever since. They've been stretched by cosmic expansion into the microwave part of the spectrum. This is the cosmic microwave background, the afterglow of the Big Bang itself, the oldest light in the universe, a snapshot of what the universe looked like 380,000 years after its birth. But before we dive into the cosmic furnaces themselves, let me give you fair warning. What you're about to learn will fundamentally alter your perception of reality. The physics we're dealing with is so extreme that it defies every intuition you have about how matter should behave. We're talking about temperatures where atoms can't exist, where electrons are stripped away and matter becomes a soup of charged particles. We're talking about pressures so intense that quantum mechanics becomes the dominant force, where particles tunnel through barriers they shouldn't be able to cross, where the very structure of space-time begins to warp and distort. The timescales are so vast that human history becomes less than a blink. While you've been alive for a few decades, stars have been shining for billions of years. While human civilization has existed for maybe 10,000 years, some stars will continue burning for thousands of trillions of years into the future, long after our sun has died and the Earth has been consumed. The smallest red dwarf stars will still be shining when the current age of the universe has passed 100 times over, and the implications, well, they're going to make you question everything you thought you knew about your place in the cosmos. You'll realize that you're part of a cycle that's been repeating for over 13 billion years, that your atoms have been through multiple stars, that you're a temporary arrangement of matter that will eventually return to the cosmos to be recycled again. The calcium in your bones was once inside a star that exploded billions of years ago. The iron in your blood was forged in conditions so extreme that they only exist for milliseconds during a supernova. The oxygen you're breathing right now was created inside a massive star that lived and died before our solar system even existed. We can't see the first stars directly because they're hidden behind the cosmic microwave background. They formed later, perhaps 100 or 200 million years after the Big Bang. But we can infer their existence and study their effects on the universe. These population 3 stars were massive, perhaps hundreds of times the mass of the Sun, and they lived fast and died young. Their supernovae seeded the universe with the first heavy elements, enabling the formation of later generations of stars. Without them, stars like the Sun couldn't exist, and neither could we. Now, let's talk about the future of stars and what it means for the ultimate fate of the universe. We've discussed how stars form and die, but what happens on cosmic timescales when you zoom out and look at the entire history of stellar evolution from beginning to end? Right now, we're living in what cosmologists call the stelliferous era, the age of stars. The universe is about 13.8 billion years old, and it's filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. Star formation is still happening, though it's declining. The rate of star formation in the universe peaked about 10 billion years ago and has been gradually decreasing since then. As galaxies consume their gas supplies and convert it into stars and stellar remnants, less and less material remains to form new stars. In about another trillion years, give or take, star formation will essentially cease. All the gas will have been either converted into stars, locked up in stellar remnants like white dwarfs and neutron stars, ejected from galaxies by supernova explosions and active galactic nuclei, or heated to temperatures too high for star formation by various feedback processes. The universe will be populated primarily by red dwarfs, the smallest and longest-lived stars, along with countless dead stellar remnants, white dwarfs, neutron stars, and black holes. The brilliant blue giants will be long gone. The sun-like yellow stars will have burned out. Only the dim red dwarfs will remain, and even they will eventually exhaust their fuel. The red dwarfs will continue to shine, but they too will eventually exhaust their fuel. The smallest red dwarfs can live for 10 trillion years, possibly longer. But even 10 trillion years is not forever. By about 100 trillion years from now, 100,000 billion years, the last star will go dark. The stelliferous era will end, and the universe will enter what's called the degenerate era, lit only by the faint glow of cooling stellar remnants. White dwarfs will fade over trillions upon trillions of years, cooling slowly as they radiate away their residual heat. Eventually, after unimaginable spans of time, they'll become black dwarfs, cold stellar corpses that emit no light. But even these aren't stable forever. On timescales far longer than the current age of the universe, on timescales almost impossible to conceive, quantum tunneling can cause even the most stable matter to decay. Protons, thought to be stable, might ultimately decay into lighter particles and radiation. We don't know if proton decay actually occurs because we've never observed it, but some theories suggest it should happen on timescales of 10 to the 36 years or longer. That's a 1 followed by 36 zeros. A trillion years. If proton decay occurs, stellar remnants will slowly evaporate, atom by atom, leaving behind only radiation and perhaps a few black holes. Black holes will be the last large structures remaining. But even they aren't eternal. Stephen Hawking showed in the 1970s that black holes slowly evaporate through a process called Hawking radiation. It's a quantum effect that occurs near the event horizon, where particle-antiparticle pairs form and one falls into the black hole while the other escapes. The black hole loses mass in the process. Smaller black holes evaporate faster. A stellar mass black hole, about 10 times the mass of the Sun, will take about 10 to the 67 years to evaporate completely. That's 10 trillion years. Supermassive black holes will last much longer, potentially up to 10 to the 100 years, a Google years. That's a 1 followed by 100 zeros. Try to imagine that time scale. The universe is currently 13.8 billion years old. That's about 10 to the 10 years. A Google years is 10 to the 100 years, 90 powers of 10 longer than the current age. It's a span of time so vast that the entire history of the universe so far is like less than a billionth of 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 the time. The largest black holes will exist. In the end, after all the stars have died, all the remnants have decayed, and all the black holes have evaporated, the universe will consist of nothing but a thin soup of elementary particles and photons spread across an exponentially expanding space. The temperature will be infinitesimally close to absolute zero, a tiny fraction of a degree above the coldest possible temperature. This is the heat death of the universe, the final equilibrium state where nothing happens anymore because there are no energy gradients to drive any processes. No stars, no planets, no life, no complexity. Just particles drifting through an ever-expanding void. But here's the beautiful and terrible thing. We exist in the brief cosmic moment when the universe is interesting. The stelliferous era, when stars shine and planets form and life can emerge and civilizations can arise, represents only about the first 100 trillion years or so of cosmic history. If the universe lasts for a Google years until the last black holes evaporate, then the age of stars represents only about a tiny fraction of 1% of the total timeline. Actually, it's much less than that. It's about 1 part in 10 to the 88. That's a decimal point followed by 87 zeros and then a 1. The percentage is so small that writing it out would require more zeros than I can reasonably include here. The age of stars is vanishingly brief compared to the total lifespan of the universe. We are living in the spectacular opening moments of a story that will last almost forever, but whose spectacular part is vanishingly brief. The universe won't always have stars. For the vast majority of its existence, from the perspective of total elapsed time, it will be dark, cold, and essentially changeless. Nothing will happen. There will be no events, no change, no complexity, just particles slowly drifting apart forever. But right now, in this cosmic instant, stars are shining, planets are forming, life is thriving, and conscious beings are contemplating the nature of it all. We're living in the golden age of the universe, the brief period when interesting things can happen. This gives stars a significance beyond their physical properties. They represent the brief period when the universe is creating complexity, when matter can organize itself into intricate structures, when energy flows create the conditions for life and mind to emerge. Stars are the furnaces that power this brief age of wonders. Without them, the universe would just be hydrogen and helium forever. With them, the universe becomes a place of planets and chemistry and life and thought. Every time you look up at the night sky, you're witnessing something that won't last forever. Those points of light represent nuclear fires that will eventually burn out. The constellations you recognize won't always be there. The stars are moving, and over tens of thousands of years, the familiar patterns will distort and change. Orion's belt will stretch and deform. The Big Dipper will become unrecognizable. In a few million years, the sky will look completely different from today. The stars will have moved enough that none of the current constellations will be recognizable. In a few billion years, the Andromeda Galaxy will collide with the Milky Way, creating a new merged galaxy and completely rearranging the night sky. In a few trillion years, there won't be a night sky to look at. All the stars will have burned out and the universe will be dark. But right now, we have this. We have a universe lit by countless stellar furnaces, where complex chemistry can occur, where planets can form in habitable zones, where life can emerge and wonder about its place in the cosmos. We have stars to guide us, to inspire us, to show us that we're part of something larger than ourselves. You are made of star stuff, arranged in a configuration that allows the universe to understand itself. Every photon hitting your eye from a distant star has traveled across space for years or centuries or millennia, carrying information about nuclear processes in stellar cores. Your ability to see and comprehend those stars is the universe engaging in a conversation with itself, matter understanding matter, light illuminating consciousness. The atoms in your body were forged in stellar cores and scattered by stellar deaths. The carbon that forms the backbone of every organic molecule in your body was created by helium fusion in the cores of red giant stars. The oxygen you breathe was created by fusion in massive stars and scattered by supernovae. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of it came from stars that died billions of years ago. The energy that powers your thoughts comes ultimately from fusion reactions in the Sunday photosynthesis, captures that energy and stores it in chemical bonds. Animals eat plants or eat other animals that ate plants. The food chain always traces back to the Sunday. Every thought you think, every movement you make, every breath you take is powered by nuclear fusion happening 93 million miles away in the core of a star. The complex chemistry that makes life possible requires heavy elements created in supernovae. You can't build complex molecules from just hydrogen and helium. You need carbon for organic chemistry, oxygen for water and metabolism, nitrogen for proteins and DNA, phosphorus for energy storage, sulfur for certain amino acids, and trace amounts of dozens of other elements. All of them came from stars. Stars aren't just objects we observe. They're the creators of everything we are. Without stars, the universe would be simple. Just hydrogen, helium, and a trace of lithium. No complexity, no chemistry, no planets, no life. Stars transform the universe from a homogeneous soup of light elements into a cosmos rich with possibility. They're the alchemists that turn simple matter into the building blocks of complexity. And the remarkable thing is that we can understand this. Through physics, chemistry, and astronomy, we can decode the nature of stellar fusion, predict the evolution of stars, and even create fusion reactions in laboratories on Earth. We're getting close to building fusion reactors that can generate power, mimicking on a tiny scale what stars do naturally. We've gone from wondering what stars are to understanding their life cycles, from fearing celestial events to predicting them with precision, from seeing stars as mysterious lights to recognizing them as our cosmic ancestors. We know more about stars than any civilization in human history. We can look at a star's spectrum and determine its temperature, composition, age, and mass. We can predict when stars will die and how. We can model their interiors and test those models against observations. This understanding doesn't diminish the wonder of stars. It enhances it. Knowing that Betelgeuse is a red supergiant nearing its explosive end makes it more fascinating, not less. You're looking at a star that might explode while you're watching it. Understanding that the sun is a thermonuclear reactor that will shine for billions more years makes sunsets more precious, not less. Every sunset is a reminder that we live in the brief age when stars shine. Recognizing that we're made of stellar debris makes our existence more miraculous, not less. You're not separate from the stars. You are the stars rearranged. You're the universe made conscious, matter that has organized itself to contemplate its own origins. Stars are the universe's gift to itself, structures that create complexity, enable life, and make consciousness possible. They're temporary, lasting only a tiny fraction of cosmic time. But during their brief lives, They transform the universe from simple to complex, from sterile to fertile, from dark to light. So the next time you look up at the night sky, remember what you're really seeing. You're seeing cosmic furnaces that have been burning for millions or billions of years. Nuclear reactions creating elements that didn't exist before. Light that has traveled across space, carrying information about processes in stellar cores. You're seeing the past, watching stellar evolution in real time, witnessing the brief age when the universe is interesting. You're seeing the stars that made you, the fires that forged your atoms, the beacons that light the cosmic darkness. And in seeing them, you're fulfilling the purpose they inadvertently enabled: conscious awareness of the universe by the universe itself. Your consciousness isn't separate from cosmic consciousness. It's cosmic consciousness, examining itself from one particular perspective, using one specific configuration of atoms as a tool for self-reflection. This means that when you feel overwhelmed by the vastness of space, you're not a tiny being contemplating something infinitely larger than yourself. You're infinity, contemplating itself through a finite lens, the unlimited using the limited as a window into its own nature. Stars aren't just balls of gas undergoing fusion. They're the reason everything exists. They're the ancestors of complexity, the engines of chemistry, the enablers of life, and the illuminators of cosmos. They're everything. And understanding them is understanding where we came from, how we exist, and why the universe is the way it is. That's what stars really are. They're not just objects in space. They're the creators of space's contents, the authors of cosmic chemistry, the progenitors of planets and life and consciousness. They're temporary structures in an evolving universe, but during their brief reign, they make everything possible. And you, standing on a planet orbiting one of these stellar furnaces made of atoms they created, powered by energy they provide, conscious because of chemistry they enabled, you are their legacy, their offspring, their gift to the cosmos. So remember, every time you feel the warmth of the sun, you're feeling fusion power transmitted across 93 million miles of space. Every time you look at a star, you're seeing into the past and witnessing nuclear alchemy. Every time you think about the cosmos, you're using structures built from stellar debris to contemplate the very processes that created those structures. You are made of stars, powered by stars, existing because of stars. And in understanding them, you complete a cosmic circle. The universe understanding itself through minds, made possible by stellar evolution. That's everything about stars. And it's everything about you, too. I wish you a very good night. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow, as always. Until then, keep looking up, keep wondering about those distant fires, and remember that their light connects you to the deepest history of the cosmos itself. You are Stardust, contemplating Stardust. You are the universe made conscious. And that might be the most remarkable thing stars have ever created. This is Boring Space, signing off. Cheers.